Hello, everyone. I'm Nashlie Sephus, and I'm a tech evangelist with Amazon AWS AI. I focus on fairness and mitigating biases in our AI technologies.
Hi everyone, my name is Krishnaram Kenthapadi. I'm a principal scientist also at Amazon AWS machine learning team, leading our efforts on topics such as explainability, fairness, and privacy in machine learning. Today we are excited to just present a talk on responsible AI in industry and share some of the practical challenges we have encountered as well as the lessons we have learned in the process. Let's start with what's been happening in the last several years. We have seen that there are several instances where biases have been observed in applications ranging from photo tagging, web search, hiring, criminal justice, and so on. Why is this happening? So this is happening because of the fact that there are inherent biases present in our society, and often these biases may be reflected in the training data or the choice of the optimization objectives, machine learning model training, and so forth. And as a result, it's not at all surprising that the machine learning models end up suffering from such biases. There has been so much awareness that there are even popular books written on these topics, like some of the books listed here. At the same time, for a long time, there has been several laws and regulations against different forms of discrimination. For example, in the United States, many of these are from the civil rights movement, especially the Civil Rights Act of 1964 and subsequent laws which prohibit discrimination on the basis of attributes such as race, gender, age, and so on. More recently, we have seen renewed attention because of regulations like European Union's Global Data Protection Regulation or the subsequent regulations such as California's Consumer Privacy Act. Often we tend to think of these regulations as solely about privacy, but if you look carefully, they also discuss fairness, transparency, explainability, and the related topics. So to kind of recap, we saw some of the motivation from the regulatory angle. We want to understand why a machine learning model made a certain prediction and whether that prediction is free from bias, both during training as well as at the inference time. There's also interest from a business or product angle, where often there is a need to provide explanations to various internal teams, whether it is loan officers, complaints teams, customer service representatives, and so forth, as well as even to the end users or customers of the product or service. Now, even from a data science or model developer angle, often there is an interest to understand which models are how to improve the models, which features are most important for the model, which parts of the data are most relevant for the model, how to debug the model, how to understand when to trust the model, what are the failure modes of the model, and so on. So given all of this, if there is one takeaway from this talk, it's that we need to think of notions like fairness, explainability, privacy, and so on by design, while designing and developing machine learning models, as opposed to viewing them as an afterthought. So let's briefly look at some of the challenges that we face when applying such dimensions: fairness, explainability, or privacy in machine learning. The first type of challenge I want to emphasize is how to scale these approaches across a wide variety of domains, applications, and customer interests. For this, I'm illustrating via the machine learning stack that's offered by AWS. At the bottom, we offer various frameworks and infrastructures such as PyTorch, TensorFlow, or deep learning machine images, containers, and so forth. At the middle, we offer the various machine learning services in the form of Amazon SageMaker, which can be thought of as a scalable platform for all aspects of the machine learning lifecycle. Then at the top, we offer various AI services for applications ranging from vision, healthcare, speech, personalization, fraud detection, and so forth. So if you take any of these layers, so first challenge is how do we provide, say, fairness or explainability functionality that caters to customers using different services listed here. The second is how do we provide this functionality in a way that applies to customers from different industries? The requirements of customers from, say, financial services may be very different from those in healthcare or hiring. And even in the same domain, let's say even in financial services, the requirements of large banks may be very different from requirements of startups, which in turn may be different from the requirements of regulatory agencies. The requirements in a domain such as computer vision might be quite different from the requirements in a domain such as anomaly detection or speech or healthcare. So this is one type of challenge, how to offer tools that are applicable for a wide range of applications and domains. The second type of challenge is the fact that often many real-world systems are highly complex. To illustrate this, I'm giving the example of LinkedIn, where I was part of the machine learning team before joining Amazon. As you may know, LinkedIn operates the largest professional network with more than 500 million members, as well as several tens of millions of jobs, companies, tens of thousands of schools, skills, and so forth. And if you take any user-facing application, let's say the feed ranking that we see when we log into the LinkedIn app, that itself is powered by several underlying machine learning models. The feed ranking is powered by machine learning models that rank the job recommendations, machine learning models that rank ads, machine learning models that rank the people recommendations, and so forth. And if you take one of this, let's say the job recommendations, that itself makes use of earlier machine learning models that map a job's free-form title to one of the canonical titles, or a member's title to one of the standardized or canonical titles, and so forth. So the challenge here is how do we reason about the fairness or the explainability or privacy of this composite system, which is composed of a chain or even a tree or directed acyclic graph of various machine learning models underneath. How do we reason about, say, fairness of the final system in terms of fairness of the underlying models? Or how can we provide explanation to the end user based on the explanations for each of the individual models? In some of these aspects, there are better solutions known. For example, we know that tech notions such like differential privacy compose well, that we can provide guarantees on the differential privacy level of a combined system in terms of the differential privacy of the individual components. But when it comes to, say, explanations or fairness, the field is largely open. There is recent research, but still there are a lot of interesting open challenges which are present here. So with this motivation, we will look at a few applications next.
Thanks so much, Krishna. So let's talk about what machine learning is not. And for those of us in the field, we definitely know it's not perfect. It is definitely not 100% confident, and it's not intended to replace human judgment. And so when we're considering our applications, these are definitely things to keep in mind. Keep in mind that the world is on the outside. The machine learning algorithm, it may seem like a black box, but there's a lot going on the inside. And we want to make sure that we understand and can explain and have reasoning behind all the different components and understanding where biases may occur at various stages. So let's discuss some specific use cases with fairness techniques and faces, which is one of my areas that I focus on. So to break it down, there are several different types of face technologies. when it comes to artificial intelligence. One is called face detection, which detects a face, whether or not a face is present in a video or an image. Another type of service or application is face analysis. And so assuming you have already detected the face or you know where the face is located, what other attributes can you pull out of that, that face? So for example, is the person wearing sunglasses? Are they smiling? Are their eyes open? And there are other attributes such as gender in terms of binary gender. We also want to make sure, however, that one, we're considering whether or not these services and the uses of these services are biased or discriminating against any particular group, such as gender, for example, only determining binary gender. Also, each one of these attributes, including the face detection technology I discussed in the previous slide, should be checked for biases. So there's bias as a whole across the system, and then there's bias that can occur in each individual attribute. And then, of course, there's face recognition, where a system can determine if faces are a match or close match, one-to-one, or if a face is actually located within a database of other faces, of n number of faces. So sort of match or ID. And so that's what most people refer to when they say face recognition. Now, sometimes these use cases can be more mission critical than in other cases. So for example, if I'm trying to unlock my phone, that can be pretty critical. If I'm trying to find pictures of my dog or my sister in my photo album, then okay, that's not so critical. However, if you have law enforcement using these technologies and they're implicating someone who is not necessarily the culprit, then that is definitely a problem that we want to look into and understand how we can guard against these biases. And one thing that's often not discussed in terms of the use of these systems, how is the user or customer using the confidence score? Every machine learning model that is trained, such as deep learning with images or text or NLP, for example, uses a confidence score that is returned. And you can take that confidence score, it's basically an indication of how confident or the certainty of any prediction. And so what we usually do in practice is we do some experimentation to figure out what is the threshold for that confidence score. Are we only accepting items, uh, predictions that are higher than 70% or predictions that are higher than 90%, for example? Or are we setting a pretty low bar in an effort to get more data returned at like 50%? So it really just depends on the application. For example, if you are using some of those more mission critical use cases, you may want to be as high confidence as possible, have as high confidence as possible. So maybe 99%. Or you may say, I want to find more people that could possibly match my criteria. For example, when trying to find pictures of my sister in my photo album, I'm okay if I include additional people, if other people get returned, because obviously I know who my sister is. And so I would lower the threshold a little bit to make sure I capture all the pictures so that I can post on social media for her birthday. And so these are things you consider when you're the user. And as companies in industry, we have a responsibility to educate people who are using these technologies. So face recognition in particular has several causes of error, even beyond, before we even enter into the bias conversation. So for example, if in computer vision, if things are not lit correctly, There's different poses or different ages, or someone's wearing makeup or a filter. Things can look extremely different. Faces can look extremely different. And so when you add on the biases, that adds another level of complexity that deserves due diligence and its rightful attention. So where can biases exist? So there are several face data sets that were in operation actually prior to about 2019 or the summer of 2019. Majority of these face recognition data sets, this was actually a figure pulled from the Fairface paper. Most of them, as you can see, in terms of race, were very much biased towards the white group. It wasn't until later, like I said, at 2019 or so, that data sets started to be created specifically for doing bias testing for race, for age, for other types of backgrounds. And this just shows a breakdown of how Fairface was able to do that. And there have been several more since then. So when you're actually testing for biases, how do you know when you're launching a product in the industry, how do you know that you've done everything that you can do to make sure that you are putting forth efforts to have a fair, unbiased system? Consider everything that's going on in society at the time. We as scientists, engineers have to be culturally relevant and up to date to what's going on the social science side. Some people even go as far to add social scientists and humanities personnel and employees to their science teams to help consider these things. But at the very least, consider how will you know if users are being harmed when you deploy? Also, how will you know if harms are unfairly distributed, particular groups, especially marginalized groups? Make sure you have very detailed testing practices. Those are often not covered in academic papers. I will touch on one paper in particular that does towards the end of the talk, but definitely consider that even after the product has been launched, because things change over time. They call it model drift. Data can change over time. Dynamics, use cases can change over time. And then lastly, discuss your testing requirements with a very specific focal point. Again, those cross-functional teams getting buy-in from other scientists and social scientists and humanities people. Also, you want to make sure that your experiments are reproducible. This should go without saying, but sometimes you'd be surprised. You can use, notebooks. For example, of course, we use SageMaker at AWS to prepare a lot of notebooks that we can reproduce and take data and reproduce the same experiments to do apples to apples comparisons with any type of data set for any particular type of service that we have or that we launch. For example, the PPB dataset, the Parliament dataset, uses a breakdown of male and female, lighter skin and darker skin. Such a notebook can help us reproduce this. We actually call it PPB2, the Parliament dataset from the Gender Shades paper, to show that we were able to get the same results or slightly different results when it came to just seeing what sort of demographics are contained in that test data set. Of course, back in 2019, we were able to do extended experimentation to understand where the biases may exist in our recognition software with AWS. And so in particular, we want to make sure that, as you can see, when performed on the Parliament dataset for previous versions of recognition on the previous version, as well as when tested on our recreated PPB2 dataset, there are large error rates and sparks on this particular dataset. And we'll talk a little bit more about how to choose those test datasets, but you want to make sure that they are fair and balanced. As you saw in the previous slide, part of the analysis involves the analysis on the data itself. And so we were able to refine our model, diversify our data even more, and get much lower error rates for the various groups. Darker skinned female, especially, darker skinned male actually looks like it stays around the same. And the error rates vary more. One additional thing you want to do is to make sure that you actually have error bars, which are not shown here, but that accounts for anytime you have data that is not necessarily balanced. And there's different types of error bars you can use, but those give a more accurate depiction of what the error rates are showing. And of course, with this data set, carrying on with this example, we were able to take the PPB data set that we created, that we recreated, the PPB2 data set, and verified that there was definitely a higher error rate, almost twice as much for darker skinned females at the confidence score of 50%. Excuse me. But again, depending on your application, you're going to want to use a much higher confidence score. And we recommend a higher confidence score of maybe 99% or at least 90%, where you can see the error rates are very similar, both under 2%. However, as you approach 99%, they get closer. But keep in mind that you also don't get as many predictions or responses when you throw out everything that's lower, that has a confidence score lower than that threshold. Sometimes this can hurt your use case. And so it's a lot of trade-offs that have to happen, and that only happens with experimentation. So with that PPB data set, we were able to show confidence scores for correctly classified samples. And a part of the process, of course, this is an older study, but a part of the process was to make sure that we actually visually inspect the data that we see, because that allows you to understand in computer vision a little bit better about what's going on. So we inspected the positive predictions for the darker skinned females. To dig deeper, we also inspected the error conditions with confidence scores. As you notice, the confidence scores are lower. And so perhaps if we set a confidence score of 99 or higher, then these errors would not have caused an actual error in our system. However, sometimes getting no answer can be worse than getting a wrong answer, or vice versa. It really just depends. I think after visually inspecting the errors, and also visually inspecting the correctly classified samples for those higher confidence scores for the lighter skinned female, and the errors in the lighter skinned female, we noticed that both the errors for lighter skinned female and for the darker skinned female, I'll go back, we noticed that these women actually had shorter hair. And this is for gender classification, binary gender classification, male or female. By the way, I didn't mention that. And so that's what the classification task and experiment is about. And so, as you can see, these women were misclassified as men. So were these women. And we said, let's take a look into the variable of hair length, because majority of these women have shorter hair. So there could be some algorithmic bias that exists in the hair length. And so that is something that we explored. Here, we gathered additional data to try to understand if that algorithmic bias holds true. So we labeled some data, 1 to 2 inches hair versus medium length versus long length versus extremely long, like past your shoulders. And we did that experiment to test that hypothesis. And what we found was that there was, on that particular data set that we created, that we did actually see a lot higher error rates for women with shorter hair, especially the lighter skin. But again, as you go closer to your threshold, if you set a higher threshold, so this would be a perfect example where you would want to set a higher threshold, all of the groups approach zero error. But still, just remember that you're throwing out a lot of data, so it makes your application, it could make it a little bit more difficult to use if majority of your predictions fall below that confidence score. So just keep in mind that efficient testing for bias, it can include development teams. They're under multiple constraints oftentimes, so bias sometimes falls by the wayside. But this is something to put at the forefront and to ensure that you're prioritizing it in terms of resources on your teams. And definitely make sure you choose your evaluation metrics in light of acceptable trade-offs, again, between false positives and false negatives. That's what I was mentioning about the confidence scores. If you set a very high threshold, then remember your false positives, you can get probably less of those, but how does that affect your application and evaluation metrics? So I did mention very briefly that I would discuss a paper that has, in my opinion, a very interesting approach towards accountability for machine learning data sets and practices for software engineering and infrastructure. This is a paper from these people mentioned here. Margaret Mitchell was one of the people contributed here, Ben Hutchinson, Andrew Smart, etc. This was actually presented at the FACT conference earlier in 2021 this year. And so I really like the fact that it really dug into how you collect these data sets. How do you, regulate and control what data is going in there? Who's putting data in there? Is it correctly annotated? Are you diversifying your annotators? Has individuals who gave that data, did they give consent? And how do you create this transparency about the data so that there's no secrets? And so what they proposed was a data set development lifecycle, which is similar and draws a lot of inspiration from the software development lifecycle. And also putting emphasis that this is something that is very important that people should consider. And it goes through all these different stages, including requirements analysis, spending time on how do you design the data set? Where do you source the data? And is it ethically sourced? How do you implement and how do you test? And then how do you continue to maintenance that over and over again in that life cycle? And then not to put these people on a lower pedestal than other people who are a part of the software development process. So my takeaways are: make sure you're testing for blind spots amongst intersectionalities, darker skinned female, younger age groups, etc. Taking into account your confidence score, you want to make sure that you set your thresholds according to your application. And there are trade-offs. Making sure that you also use error bars when measuring for biases. Remember, representation matters. Diversity on your tech teams, diversity on your product teams, or even tapping into focus groups that can help you get those diverse perspectives is extremely important, from different groups to represent their opinions and their perspectives. And I will say to make sure that we adequately compensate those people for their time in some way. Transparency, reproducibility, and education can promote change. Absolutely, it can on your teams. Confidence in your product's fairness requires fairness testing. You cannot assume what you have not tested. Remember that fairness testing has a role throughout the entire product and iteration lifecycle, and the same for the dataset lifecycle. Also, contextual concerns should be used to prioritize fairness testing. Different applications require different types of testing, and every piece of the system should be tested or at least considered as to whether or not it needs to be tested. I'll now hand it back over to Krishna.
Thanks, Nashlie, for that nice overview. Next, I want to give a case study where we offered tools to detect bias in machine learning models and also to help explain or understand model predictions. This is a functionality that we called Amazon SageMaker Clarify, which is a functionality that we launched during December last year as part of Amazon SageMaker. As I mentioned at the beginning, SageMaker is a scalable platform for doing data labeling, model training, model tuning, model debugging, model deployment, monitoring, and so forth. In other words, addressing all aspects of the machine learning pipeline. In SageMaker Clarify, we offer the following functionality. We provide tools to help identify biases in the training data as part of the data preparation stage. Then we offer tools to check the trained model for different types of biases. In other words, measure whether the predictive behavior of the model is the same or is similar across different groups of interest. Similarly, we provide functionality to explain the behavior of the model as a whole, as well as explain the individual predictions made by the model. Finally, once the model has been deployed, it's important to understand whether the bias or the explanations of the model drift or change over time. And we provide a functionality as part of SageMaker's model monitor component to provide alerts whenever such a drift is detected. And such drifts can occur due to changes in real-world conditions over time, changes in the distribution that is queried to the model or other conditions over time. Finally, we also help generate automated reports, which can be then shared with other relevant stakeholders. So let's look at a brief case study of how this is used in practice. So for that, let me show the parts of how SageMaker Clarify is used. So first, this is one can use SageMaker Clarify as part of the data preparation. So for this, here we are importing a data set which is called the German credit data set. Is a publicly available data set about lending and credit history. And once the data set is imported, we can then measure biases in this data set. So we can choose one type of analysis called bias report and select the column which corresponds to the label, in this case, whether somebody has good credit or not. And then we can also select the column which corresponds to the sensitive attribute. In this case, we are selecting age as the attribute, and we are considering that age above 40 versus age below 40 is or the two buckets of interest. Then we can select different bias metrics which are influenced by various requirements in financial and other industries. And once we select this in near real time, we can then compute the bias metrics over this data set. Here we see bias measures such as class imbalance and other metrics. And we also see how they fall within the possible range of each of these metrics. And if needed, we can then click further and see illustrations of what these metrics mean and some examples or motivation of why one might want to care about these metrics. Next, at the time of once a model has been trained, we can do this similar measurement of biases. So here I'm going to show jump to the user experience part of this, where we can see again different bias metrics of how the predictive performance of the model differs across different groups. And then again, once again, you can click on any metric and see further explanations and examples of where that metric may be relevant. And we can also see how the observed value falls within the range, allowed range. Um, and likewise, we can also see um, uh, which features are most important for this model. So we can take a look at of different features which are present in the model. Which features are most important? I think it's there in one of these screenshots. Next, uh, beyond data preparation and model training, it's also important to understand how the bias varies once the model has been deployed. And to do this, what we can do is we can select one of the deployed endpoints of the model and and then measure whether uh, the set of important features or the bias metrics are changing over time. So in this case, these are the metrics which are the top 10 features for the model, and we can now observe whether yeah, how this feature importance changes over time. So here we are checking whether over the duration of 1 week, uh, we select one of these features and how that importance has changed over time. So we can see that the feature importance is in the range around 14% and changes a little bit over time. We can also see whether the overall importance, so the overall importance also changes over time. So we can do similar studies for the various bias metrics as well to understand whether the bias, observed bias, exceeds some allowed threshold, and if such drift is detected, then we can trigger alerts, and the data scientist can take some actions based on these alerts. And this is just a brief illustration of how we can apply tools like SageMaker Clarify on data sets like the German credit data set. Next, I want to just briefly go into some of the lessons we learned in the process. One lesson that we learned talking to several customers and developing this product functionality is that notions of bias and fairness are highly application dependent. The attribute or the attributes that one may care about may vary a lot depending on the application of interest. And both such an attribute as well as which bias metrics to focus on need to be driven not by, say, computer scientists or broadly people with technical backgrounds, but also by looping in all relevant stakeholders. These can include people with social science background or legal background, as well as other non-technical considerations. And closely related to this, we need to take inputs from all stakeholders involved. These include, say, people from different disciplines, as well as the end users and affected communities who may be potentially impacted by the machine learning model deployment. Next, it's also important to notice that there may be a spectrum of customers with different levels of technical background. This is one motivation for us to offer a managed service versus a customer having to go and make use of an open source package and install that package, debug or set up that package themselves. And the other part, as I mentioned before, is that it's important to not only measure biases during model training or data preparation, but also monitor the model once it's deployed for any biases that might arise over time. And more broadly, it's important to think of such considerations across the entire machine learning lifecycle. Let's see what we mean by this. Starting with problem formation, we need to ask ourselves, are we applying machine learning techniques in an ethical manner? Is an algorithmic approach even an ethical solution to the problem? Should we even be solving such a problem in the first place? The second is at the time of data set construction, we want to understand whether the training data is representative of different groups. Are there any biases in labels or in the data distribution? Do we need to apply debiasing techniques? Do we need to collect more data and so on? Then the second is at the time of the machine learning model training, we need to ask whether any fairness constraints have to be included as part of the objective function. Similarly, like at the time of testing, have we evaluated not only with respect to accuracy or error, F1 metric and so on, but also with respect to different fairness metrics. Yeah, at the time of say A/B testing or deployment, we need to understand, are there unequal effects across users? Even if a new model is providing better business metric overall, are these effects distributed similarly across users? Is it the case that the model is providing improvement for a small fraction of users, but for a large fraction of users, there is a degradation in performance? Yeah, similarly, like, are we deploying the model on a population for which it was not trained or evaluated for? And once we deploy the model, we need to check whether there are any feedback loops that can potentially result in unfair outcomes over time. These are some of the lessons we learned in the process of developing SageMaker Clarify and deploying it over the last several months. If you're interested in more details, please refer to the SageMaker Clarify product page, or we have a couple of technical papers, including an upcoming KDD 2021 paper on the SageMaker Clarify system and the lessons learned in the process of developing the system. And let me conclude this talk by emphasizing that we need to think of fairness, explainability, privacy while building AI and machine learning products, and need to collaborate and take inputs from all relevant stakeholders into account. And let me leave you with the following thought. It's good to think in terms of what's called a front page test. Even if we are working on some systems which may not be end user facing and which may be hidden underneath, if there's a front page article about that component, we would feel uncomfortable. Then it's a good time to pause and ask ourselves, is there something we need to be applying with respect to fairness or explainability or privacy? Should we have appropriate conversations with maybe subject experts or people from other disciplines who may have inputs to offer to us? So with that, let me conclude, and we'll be happy to get your feedback and discuss questions during the Q&A time. Thank you.